So this is a second webinar that has been conducted by learnSAx. This webinar is for application of CFD for rotating machinery flow analysis. This is an introductory webinar where we will study some of applications of CFD for modeling flows through rotating machinery. We will not go much into detail of theoretical or case study or technical results, but we will focus on how CFD is applied to rotating machinery flow analysis and what a fresh CFD engineer or someone who is new to CFD should know in order to get into this field of modeling rotating machinery flows using CFD. So that just introductory information that is required will be given, and so that someone develops much more interest in modeling CFD for rotating machinery flow or turbo machinery flow. So let us begin our session here. We will just have a short look at the roadmap that will follow for this particular webinar session. We will have a short welcome and introduction at the beginning. Then we will proceed with the webinar presentation. At the end of the webinar presentation, we will take your questions. And we'll end the webinar presentation or the webinar session by giving you short or brief information about our training activities or anything that interests you within our training portal. So before we begin, thank you for your registration for this particular webinar and for attending this particular session. This is an introductory webinar, as I just said, on CFD modeling for rotating machinery. It is a second webinar among the series of webinars that learnSAx will conduct. We will continue to conduct more interesting webinars even after this, and you can register for them free on our training portal. You can also sign up on our training portal for free resources related to CFD. This webinar is designed to act as an introduction to CFD analysis for rotating machinery flows. So for anyone who is new to CFD or who has just entered CFD field and wants to know some more applications of CFD and how CFD is applied to turbo machinery flows, this particular webinar is designed for such participants. If you already know a lot of CFD and you know how to model rotating machinery flows, then you may be knowing a lot of this content already. So about learnSAx. learnSAx is actually a training initiative or a training portal of training division at CC Tech, that is Center for Computational Technologies. We have industry focused courses for CAD as well as CFD on our training portal. All our training is available online and you can participate or undertake our training sitting at your home just using your home internet connection and your home PC. All the resources are delivered at your doorstep using internet. So our model helps participants to learn complex technologies with ease at a time and place of their choice. So all these lectures and all the training courses are delivered through our training portal or training system. So we will have an overview of this particular presentation before we begin. First, we will discuss rotating machinery, what sort of flows are present within rotating systems, how rotating machines are classified. Then we will see how CFD can help in modeling rotating machinery flows, how CFD is applied, where can CFD play a part in modeling flows through rotating machines. After that, we will see how CFD is applied for rotating machinery, what sort of design optimization processes followed. We will have an overview of this particular process. After this, we will discuss some CFD modeling approaches that are followed in order to model the rotating machinery flows. At the end, we will give introduction or brief information about our CFD training activities, and we will take questions to end this session. So let us begin and see what rotating machinery are present in chemical or mechanical processing industry that we are either aware of or we see daily in our industrial activities. So compressors is one of them. It is meant for transport of gases at increased pressure. You can see some of the rotating machinery images out here where you'll see casing of pumps, impeller blades, the blade profiles, as well as some CFD images or CFD result images of some mixing blades type of application, as well as some centrifugal blower type of application. So turbines is another type of rotating machinery, which is a rotary device which extracts work from working fluid. Fans are used to transport gas at high volume flow rate as well as low pressure. Pumps transport fluids, mainly liquids, at increased pressure. Blowers deal with gases at high pressure. Now, other than all these equipments, there is also something called as mixing tank, which basically have impeller rotation, which causes stirring action for chemical processing, chemical reaction processing. So this is also another application of rotating machinery flow, that is mixing tank. Now basically the function of a rotating machinery or a turbomachinery is to add or extract work from a fluid. Other use, as we just discussed, can be of mixing fluids for chemical processing. All these standard equipments or turbomachinery equipments consist of moving fluids and rotating blades. This is a standard type of assembly or standard type of parts that we see in every rotating machinery. It consists of a stator and rotor. Rotor consists of blades which are rotating, and stationary part forms the stator type of part. So these devices which extract energy come under the category of turbines. So turbines convert the working fluid energy into some other form of useful energy, whereas other devices which add energy to the working fluid like pumps, fans, compressors, these all devices come under the category which add energy to the working fluid. But all these devices like turbines, pumps, fans, all these rotating machinery devices come under the generalized category of turbomachinery. These devices are also classified among them depending upon various criteria or physics. The first criteria is physics or the fluid that is present. The next criteria is direction of flow. Now based on physics, these rotating machines are classified on which type of fluid they work upon. The fluid can be compressible. Examples of such equipments or such turbomachinery are engine aircraft engine, stationary gas turbines, steam power plants, high-speed fans, etc. Whereas there are also turbomachinery equipments which handle incompressible fluids like pumps or hydraulic turbines. Now other classification which is commonly used is based on the flow direction. The first among them is axial flow devices. In these, the fluid flow is roughly along the direction of axis of the machine. The next classification is centrifugal flow devices. In these, the fluid flow direction has a radial element, and hence they are referred to as centrifugal flow machines. There are also devices which have mixed type of flow, which are known as mixed flow devices, which have both axial as well as centrifugal components. Now, after an overview of in general what turbomachinery consists of, we will see how does CFD apply to turbomachinery. Now, where can CFD help? When we say we are going to model flow through we are going to model or simulate flow through turbomachineries, where does this come, or where does this CFD modeling form part of? Now, before CFD modeling was applied, the conventional design process of any type of turbomachinery equipment was based on application of empirical design methods, wherein theoretical empirical configurations were used, the velocity triangle theory was used, and all these devices were designed using empirical design methods. Design of turbomachinery in general involves large number of variables, and different design configurations are possible in order to meet the requirement. Study or parametric study of all these designs forms a part of conceptual design process for any turbomachinery equipment. Now CFD is increasingly used to successfully design any type of turbomachinery, as well as carry out analysis and validation requirement for existing design. So CFD is used during the conceptual design process as well as after the design process in order to validate or rectify a particular design. Examples of some of the CFD applied to turbomachinery equipments are the images below show such examples like mixing equipment, also mesh around the blades that is shown here. What information can CFD can give for rotating machinery analysis? It can give you performance prediction of an existing design, wherein you can have the pressure drop versus flow rate type of curves, all the performance curves, NPSHR type of data for pumps, and many such analysis for different type of turbomachineries. We can actually have an internal flow visualization in the form of pressure distribution, flow path through impeller, diffuser, and various other components that form part of a turbomachinery equipment. Qualitative as well as quantitative validation of performance can be done using simulation. And also investigation of a existing design can be done, wherein we see using CFD analysis where do we have problems with different type of flows that are present, how can we rectify already a design that has some type of fault. So all these purposes can be solved using CFD analysis. When we say that CFD analysis is used in design process of a particular rotating machinery equipment, there is a standard CFD process which is called as optimization of design. In that process, what we do is initially we start with a initial design, we generate a CAD geometry out of that initial design. After that, we mesh that particular CAD geometry. Then we define a CFD problem, that is we define what sort of flow rate are we going to consider for that particular problem, what sort of RPM are the blades rotating with. So we define a CFD problem. After that, we solve that CFD problem using a CFD package. Then we go on and do post-processing of our results. From these results, we can draw various performance-related data, and if this meet our specified requirement, we can actually conclude that the design is correct or optimum. If it does not specify, if it does not satisfy the specified requirement, we go back to the geometry stage, we change the geometry or the design, and we repeat the entire process, and we continue this process wherein we carry out different number of parametric CFD simulations, and we zero in on the optimum design which satisfies our requirement. All these analysis can be done before the prototype stage, so it saves our time and cost actually, because we can do all these parametric simulations and we can zero in on the right design by CFD instead of doing experimental prototype analysis. So this is a CFD cycle or a design optimization cycle using CFD. Now we have studied how CFD is applied to turbomachinery and what data can CFD extract from any type of model or analysis. We will now see what are the modeling approaches. When we say that turbomachinery consists of rotating parts and it also consists of stationary parts, the blades are rotating. Now how does a CFD model or how does a CFD simulation takes care of this rotating effect? A concept called as moving reference frame is utilized within a CFD model. What it does is that it defines a frame or a reference frame that has motion relative to a stationary coordinate system. So there is a reference frame which is moving with respect to a stationary coordinate system, and the motion of this reference frame takes care of the rotating effect of the blades. Inherently, when we say that the blades are rotating, that makes a problem unsteady or transient type of phenomenon. Now in order to simplify this transient phenomenon is transformed into a steady state or a time independent phenomenon by using this rotating reference frame or moving reference frame. This moving reference frame is given a rotational velocity which is similar to the velocity of these blades or rotational velocities of these blades, and therefore looking from the rotating reference frame, this becomes a steady state type of problem. So a MRF or a rotating reference frame approach converts a unsteady flow field into a steady flow field. This steady state problem or a transformation of a unsteady problem into a steady problem makes it easier to specify different boundary conditions, to define a simpler CFD problem, and it also takes less time as well as computational efforts. So this is a concept that is utilized in order to capture the rotational effect within any type of turbomachinery CFD model. When we solve this particular type of moving reference frame, the mass momentum energy equations that are solved within a CFD model, those are still solved for stationary frame. Because of the moving reference frame model, an acceleration term comes into picture of the fluid in the moving frame, and this acceleration is defined using the relative velocity of the reference frame or the moving frame with respect to the stationary frame. The convective terms and the source term within the momentum equation, that is the original Navier-Stokes and momentum equations, these are modified using the acceleration terms to take into effect the mass flux and the momentum flux generated because of the rotational effect. The first among the approach or the models that is used for analyzing or simulating the rotational effect is a single reference frame model. As you can see, this is an example of a single reference frame model. This particular image is a 2D pictorial representation of a sort of rotating blade surrounded by its ring casing. This ring is stationary, whereas these blades can be rotating in either of the directions. Looking at this, if we define this entire volume within a rotating reference frame, other than this volume, there is the stationary part is only this ring surface. So this entire particular volume with rotating blades can come under a single reference frame which is rotating with respect to a stationary reference frame. So a moving reference frame is defined within this model of a single fluid domain. This domain moves with the frame speed around the axis of rotation, which captures the rotational effect of these blades. The stationary surface, that is this boundary, forms part of a surface of revolution. So this moving frame takes care of the rotation effect, and this surface of revolution is defined as a stationary wall. So it also can be modeled using a periodic type of model. Next particular approach is the multiple reference frame approach or a frozen rotor stator approach. An example of multiple reference frame approach is shown for this particular 2D type of blade configuration, where these blades are again rotating and the casing, ring type of casing, is stationary. Now this multiple reference frame approach is used when stationary components are present which cannot be modeled as surface of revolution. Now as you can see, this ring can be modeled as a surface of revolution, but these blocks that you can see in a 2D representation are basically baffles. So these baffles are not surface of revolution, and hence we cannot include a single rotating reference frame. What we have to do is surround these blades by a multiple reference frame zone or a moving reference frame zone, and then the rest of the volume is taken in stationary, and these baffles also form as stationary components. So what we do is we consider two distinct zones. One is a rotating zone, which is the central rotating zone, which is rotating with respect to the moving reference frame. So the entire reference frame with respect to which this inner zone is defined is rotating, whereas the rest of the zone is stationary. This forms an interface between a stationary zone and a moving zone. All the velocity vectors and velocity gradients are transformed through this interface, passing from the rotating zone and capturing its effect into the stationary zone. Flux, momentum and energy and other scalars are exchanged at this interface. Now an important criteria is the interface should form a surface of revolution. Also, it is important to note that there is no actual motion between the domains. What we mean by that is these zones that you are seeing, these two different zones, they are not moving with respect to each other. Only the rotational effect is captured by using multiple by defining a rotating reference frame. The blades cannot be seen that they are actually rotating. Its rotational effect is incorporated into the model using a moving reference frame, which is defined for this particular inner zone. More complex approach than the multiple reference frame is the sliding mesh approach. It is also computationally extensive because mesh movement comes into picture. We are taking the same particular problem where we have the inner blades which are moving. There is an inner zone which is called as moving zone, and the rest of the geometry is stationary. There are baffles present which are modeled as stationary components. So our domain is again divided into rotating and non-rotating zones. The inner zone is rotating zone, whereas the rest of the components or rest of the volume is a stationary zone. This interface that we are seeing, that is a dotted circle, is a non-conformal surface of revolution, which means that this interface is actually sliding or actually rotating. Now in this particular sliding mesh approach, there is relative motion between the zones, and hence since the motion of blades is involved, this particular approach is transient. That is, it is a phenomenon which is changing with respect to time. So during the simulation, this particular motion is actually seen, or these plates are actually moving and the mesh is also actually moving, and the interface is sliding. The outer zone is stationary. The mesh is moved during each time instant or step, and the fluxes that are calculated because of the flow as well as the motion, these are modeled at the sliding or moving interface. This interface, that is the dotted line you are seeing, is actually sliding or moving interface. Now once we have seen that, we will see the mesh criteria, or how mesh of a turbomachinery equipment, when we model CFD, how it is important. Mesh generation is especially important for any type of flow analysis within a turbomachinery or rotating machinery equipment. It is also comparatively complex than any type of simple pipe flow or simple CFD model. There are impellers or blades as well as diffuser volute. All these regions have their distinct geometrical shape or profile. These have to be captured using meshing. Casing, impeller and diffuser required separate meshing strategy. All these different meshing strategy or meshes are then merged to form a single complete domain for CFD. Hybrid mesh with tetrahedral and hexa elements are usually used. There is also something called as prism layer, which is used in order to capture the turbulent flow phenomena occurring along the blade profiles. An example of mesh for this particular application is shown here. We have a particular impeller with blades, and you can see the mesh which is captured in between them, which is generated in between them to capture the exact flow region. Also near the blades, you can see the mesh is actually varied in order to capture the blade profile. The mesh should be usually oriented along the flow direction. So all these complex meshing concepts have to be used in order to generate a very good quality mesh to capture the flow. So meshing forms a very critical part of any type of CFD model that is made for any type of turbomachinery flow analysis. Now we will just see a short pictorial representation of a 2D blower problem, which is solved by using MRF approach as well as the sliding mesh approach. These are just the primary images of some results to just show you or highlight how CFD results can look like for such particular type of rotating machinery flow. We are considering a 2D model of a standard shape centrifugal blower. It has 36 bladed impeller, which is these are 36 number of blades. Total pressure at inlet is 180 pascals. Outlet is at ambient condition, and the blades are rotating in clockwise direction by 300 radians per second rotational speed. So the flow actually comes through this section. It passes through these blades which are rotating, and the flow is forced out of the outlet. So this is the blower type of application that we are going to see, and we will see some type of pictorial images which are preliminary results for such type of flow analysis. We can solve this problem by using MRF approach, where we can actually define a moving reference frame in this ring type of zone, which is actually around the blades. So in MRF approach, these blades are not moving, and the mesh is also not moving, but the motion is incorporated by using moving reference frame. The reference frame is actually moving with respect to the stationary zone by using the rotational speed of 300 radians per second. This is the first approach, that is MRF approach, whereas in the second approach, that is sliding mesh approach, these blades are actually moving. The mesh is actually also rotating with the rotational speed of the blades. So we define a region around the blades which is called as moving zone, and these blades motion is captured by actually motion of the blades, and interface between the stationary and the rotating or the moving mesh is actually the sliding interface. In the MRF approach, there is no mesh movement, whereas in the sliding mesh approach, the mesh is actually moving with the rotational speed of the blades. You can see the mesh movement for the sliding mesh approach by just this pictorial representation of the mesh movement. This is a sort of animation. So as you can see in the sliding mesh approach, there is motion of these blades. So the blades are actually rotating, the mesh is also moving or rotating. So this type of mesh motion is usually present in case of sliding mesh or moving mesh applications. So the rotational effect or the rotation of the blades can actually be seen, whereas in the MRF approach, only the rotational effect is incorporated by using moving reference frame. There is no physical rotation of the mesh or the blades. So this is a sort of just an animation view to let you know that how the mesh motion or the blade motion happens within the sliding mesh approach. A mesh for this particular 2D geometry is highlighted here. Near the blades, we are having a finer mesh in order to capture the blade profile, as you can see in the zoom view of this particular mesh. This is the overall mesh, which is comparatively coarser. Only the region around the blades is captured using finer mesh. So just some of the pictorial images of the results. The left side is MRF approach, and the right side is a time instant image of sliding mesh approach, which is taken after 4 to 5 iterations. You can see almost similarities between the two approaches, but sliding mesh approach is actually unsteady type of simulation or transient simulation, which takes more time. It is also computationally expensive. Some detailed features are captured better with the sliding mesh approach, like this particular pressure drop region as well as region near the interface is captured better. Also, the velocity distribution is shown in this particular image. So both approaches are actually similar in terms of results accuracy, but sliding mesh approach gives you a transient type of simulation and captures results at various instants, whereas MRF approach is a steady state approach which gives you a pictorial representation of rotation, and rotation effect is incorporated by using steady state approach. So with this, we end our session of CFD modeling of turbo machinery out here, and We will, before we close this session, we will just give you information or introduction to our CFD training activities. I hope this particular session till now, which was focused on how to apply CFD on turbomachinery, rotational machinery flows, and what sort of inputs are required for using CFD, what data can be extracted using CFD, and this was a sort of CFD introduction to rotational machinery flows, and I hope it was useful for you to understand how CFD is applied to rotational machinery, what data it can give, and for detailed analysis of this, we can give you further information of how CFD can be applied or how in detail CFD can be used. So you can contact us for that. Now, regarding our training activities, we actually give training in introductory as well as advanced courses. But before that, if you are new to CFD, this is just a slide which reviews what sort of expectations can a fresh engineer keep from CFD field and what sort of skill set is required in order to do CFD analysis for someone who is new to CFD. Fundamentals of fluid dynamics and thermal sciences, such type of knowledge is always required. Fundamentals of CFD is required. Also, it is required to know how to use a CFD software. How is CFD used in design analysis is something that is very very useful knowledge. How to make sense of CFD results that we have, how to make physical sense of this, how to extract physics out of those results. It is also useful to know how to make design decisions based on CFD results. So all these skill sets can be developed by using some sort of training or self-learning. Now, most of the training of CFD is based in class, that is classroom trainings are very common, but these training have their limitations in terms of syllabus, in terms of travel and rigidity that is associated with their schedule. So instead of going into these, what we have developed or we are offering is an online training platform. This online training platform brings all these CFD lectures to your right at your desktop using just an internet connection and a computer. So all these lectures are delivered through a learning system. You can go through these lectures multiple number of times, understand them, ask questions to us. You can also have interactive sessions where our engineers or faculty will actually be online from here, and they will interact with you, clear all your doubts, help you with some of your existing doubts and problems. And this model that we are trying to develop is some sort of a combination of in-class interaction as well as online training. So this is the best possible module that we are trying to develop here, which involves no travel. So all the resources at your desk in a cost-effective manner. It is much cheaper than the in-class training that is offered. You can go through the material any number of times. You can also have interactive sessions with our faculty or with our engineers here using WebEx. Yeah, there is a set of lectures that is present as well as tutorials which are recorded, and you can view them at your own comfort, at your own time, with your own busy schedule that you have. You can view them side by side. There is no limitation of time or attendance that you have. So instead of getting stuck into the rigid in-class training, this particular training that we offer is a very cost-effective and efficient way in order to get trained in your CFD skill set. You can always visit our website for this. Currently, we are offering 4 courses that are offered online. First is CFD modeling using ANSYS Fluent and ANSYS ICM CFD. This is a 6 weeks course which can be taken online, and it imparts proficiency in CFD modeling using ANSYS ICM Fluent and ANSYS ICM CFD. Also, we offer advanced course on multi-phase flow modeling using ANSYS Fluent. This is a 4 weeks course which is an advanced course which enables you to gain the techniques of modeling multi-phase flow using commercial CFD software, that is ANSYS Fluent. Similarly, we have a heat transfer course which is again an advanced course which enables the technique or helps you gain the techniques or models which are used for heat transfer modeling using ANSYS Fluent. There is also a computer-aided geometric design course. This is again an intermediate course which focuses on fundamental core and advanced topics of computer-aided geometric design. This is a CAD course. Also, it is a development-based course, so a programming training is also involved here. So these courses are currently offered. We are also adding more courses which are based on turbomachinery flow analysis as well as other topics like combustion, etc. So how to reach us for any of your queries or any of your training interest? You can always visit our website, that is learnSAx.com. You can have a free sign up. You'll be able to view various free knowledgeable video sessions or FAQs that are there. You can also register for any of our webinars, that is free. You can also visit our blog, that is blog.learnSAx.com. You can like us on Facebook, and there are various updates on Facebook and other social medias like Twitter. YouTube, you can view our demo lectures and our demo videos on YouTube also. The best way to reach us for any of your queries, irrespective of whether you are interested in training or not, is to email us at info@learnSAx.com. So this is our central email address where you can just write any emails to us related to CFD or any queries that you have. If you are interested in training, this is the best platform that you can contact us. That is info@learnSAx.com. So we are ending our session here. Before we end, we can take your questions through the chat box. You can also contact us with any of your questions on our email address later. So we are ending our session here. Thank you for attending this particular webinar. Thank you for the registration for this webinar and sitting through this webinar. I hope it gave you an introduction of how CFD is applied to turbomachinery and what sort of applications are present in CFD, or it developed at least more interest into the field of CFD. So thank you for attending this particular webinar. See you in the next webinars that we conduct. Do not forget to register for our future webinars or on our website. So have a nice day, and thank you for attending again.